Hi, this is Will from QED, and I'll be making a presentation today about using the AfSIS DB API. To demonstrate the usage of the API today, I will be using the files that can be found on our GitHub repository at the URL shown on the screen. So I'll be walking through this Jupyter notebook, and you're welcome to download it and try to follow along, or you can just watch the video and try running the programs yourself later. So for those of you who are not familiar with Jupyter notebooks, this is a really neat technology. It's a derivative of IPython notebooks, which themselves were actually a clone of Mathematica notebooks. The Jupyter notebook runs in the browser. So when I download the notebooks in my GitHub repo, install the dependencies, and launch it, it will launch in a browser tab. And it's a little bit beyond the scope of this video to explain how to set up your computing environment to do that. But if you need to learn about that, I suggest you please consult the internet, or you can contact me separately afterwards. So as you can see, the Jupyter notebook looks a little bit like a book. You have a table of contents. You can jump to particular sections. And we have text here that's actually written in Markdown format, which is a very convenient shorthand way of marking up documents with all kinds of common styling that you may have seen on GitHub before. And you have these markdown cells, as shown here, markdown, but we also have code cells. This is a code cell, and this is actually functional. It's running our code. So each of these code cells is a small REPL, read, evaluate, print loop. So I could write some real code here and get an answer. So this is a really convenient way of interspersing your code and your flavor text together to produce a fully functional report. And it's increasingly popular amongst data scientists who wish to report what they did. So returning to the topic, I'd like to first remind everyone what AfSIS DB is about. AfSIS DB is a data management system for soil laboratory data, which we have developed for the Africa Soil Information Service. It has about 5 key features. First of all, it provides a place to store your data, and this storage is built on a relational database, namely Postgres, and there's also storage of binary blob data, such as spectral files, which goes into S3 for more efficient and cost-effective storage. AfSIS DB also provides you with a web interface for uploading your data, and there is support for server-side input validation so that it can check whether or not wavelength settings are off automatically when Opus files are uploaded to it. There is a web interface for searching and exporting data, including API support, which is the topic of this presentation. You can also link your laboratory data with field metadata collected using mobile survey. And you have access control for groups and public versus private data. But with AfSIS, we encourage all the data to be public if possible. And this whole system runs through your browser, so we don't have to worry about cross-platform compatibility problems. As far as I know, this is the largest online database of African soil data. It has currently about over 175,000 records as of the time of this video. So the website is right here, afsisdb.qed.ai, and if you want to register for an account, you just submit a request on the homepage of this site. Now there's a lot that can be shown about how AfSIS DB works. This is the actual interface. When you go in, you can see the various data tables available to you, what chemistry, soil moisture, and so on. And we have a whole separate video, which should be the prelude to this video, that explains how to go about using this software. So if you are new to AfSIS DB, please check out this other video first. And it's called Introduction to AfSIS DB. You can just go to YouTube and type this Introduction to AfSIS DB. I'm sure we're the only link. And you can watch this video. It's about 20 minutes long, and it goes through all of the main features of AfSIS DB as of December 2016, and also explains things like how to upload data and how to search for data using the web GUI. So one thing that was missing in that video was how to export data in mass. Because maybe you're doing some kind of data analysis and you need a big chunk of data that you want to stack with some other data and build some algorithmic data models. So in the browser, the way you would do this is first you would click on the type of data you're interested in. So let's say we're interested in these spectroscopy opus records. And here I see there's a lot of TANSYS records here. And I can filter them. Because right now we see that there's 146,830 spectroscopy opus records. And maybe that's too many. So I want to narrow my search. So as you can see, let's say I only want measurements that were taken using the FTNIR MPA machine. So I'll add this to my filter, click filter, and you can see there are much fewer results now. There are 722. So this shows you how you can narrow down your search results, and you can also add more search parameters as shown here. So then I can say I want to batch download all of these guys, right? So I'll select them. I selected them by clicking on this checkbox, and it selected 20, but there are actually many pages. So then AfSIS DB asks me, do you actually want to select all 722 spectroscopy samples? And let's say yes, I do want to select all of those. And I'm going to batch download them, so I'll click go. And then AfSIS DB, well, you see it says your archive will become available here. So this forks a process where AfSIS DB is gathering the data from S3, and it will let you know when your exports will be available. So I can click on here, and you can see it's not ready yet, but in time these 722 records will be gathered and made available to me in a zip file. And now 1 minute later, after refreshing my screen, I see that the zip file is here. It says ready, so I'll click on this guy, and a standard dialog will pop up asking where do I want to download this stuff. So I'll click save, and here it's downloading about 110 megabytes for 722 records. So just to save on my internet, I'm going to cancel this download, but it's basically a zip file full of binary opus files when you unzip it. Now the subject of this presentation is how can we do these kinds of download requests using a programmatic interface such that you don't need to point and click on all of these things. So that's the purpose of the API, or Application Programming Interface. The Application Programming Interface is something all developers like because it allows them to not have to worry about all of the implementation details for how some software or web server works, and just abstract away only the bare essential inputs that you need to supply in order to get certain outputs. So we have an API that is built into AfSIS DB. After you log in from this screen, you will see in the lower left corner here there's an API docs link. And if I click on it, we will see a automatically generated and interactive documentation for the AfSIS DB API. And we are actively trying to improve on this API. So yeah, your feedback is welcome. But as you can see, for each type of data, we have a corresponding API. So for the georeferences, we can explain how to get this data. You can fetch it by something called PK, the primary key, if it's known, or you can search using a much more detailed set of parameters, and it will try to compute the intersection of all these parameters that you specify and return the resulting list. So we have this for many different types of data. Currently the spectroscopy data is stored in the simply named sample, but I hope to change this so that it's more explicit and reads as spectroscopy. So just to give a simple example, let's say we want to find the TANCIS data. So we'll type TANCIS as the group, and then I'm going to try it. So I'm going to click this button, and you can see the response to the query. Right? So these are all records of soil samples that are affiliated with the TANCIS group. We can see the soil sample number, which is the SSN, the machine type, subsample ID, which is like a aliquot, the scan date, a automatically generated link to where you can download the binary file that corresponds to this record, the opus file that is. And is it public or not? Yes, it's set to public, and this is the group, and so on, right? So that's the structure of the response body, and we can see here that there are 18,186 samples that have been uploaded by TANCIS so far. And the results are also paginated in order to help control the size of the response. So if you want to go to the next page of results, you would have to make your program invoke this link. Furthermore, the documentation also shows you how you would make this API call using some programming language. So curl is a very popular tool that you can use for sending GET requests, for example, or even POST requests to the internet. So this is how you would set up the headers, CSRF token, and the query. And this is the request URL. These are the response headers. And the response code here is 200, which means OK. Bad codes are things like 403 or 502. So that demonstrates how you can interact with the API through the website. But now, going back to the programming world, you don't want to point and click on things, maybe, because for some people that's too slow. Or you have some application where you really need to automate lots of things, so there just can be no room for a human in this loop. So that's where we start writing things in a programming language, and here I'll be using the R programming language. So the first thing you'll need to do is store your credentials somewhere, your username and your password, because the computer needs to know that so he doesn't have to keep retyping that in manually. And by default here, the code is expecting your username and password to be in a file called config.ini. Okay, now that's very arbitrary, but the only thing that was important there is that it looks something like this. Your username and your password, a very simple text file. Okay, so I just put that file in the same working directory as my notebook. Now we'll go back to the code. So the next step is I'm going to install some common R packages. HTTR is often used for working with different kinds of HTTP verbs like get and post, and I think it actually installs JSONLite as a dependency already. Lubridate is used for some date-time manipulation and arithmetic, and PLYR is a popular toolkit that's being used for dataset manipulation. Another one is DPLYR. And it does things like split, apply, combine operations, but it tends to use some idioms that are a little more unified than what comes in the base R. So I've already installed these packages here, and I'm going to invoke them. Okay, so next I just have a little remark on the full API documentation is available by logging in and then looking at this link, and you can see the same kinds of screens we saw before. Okay, so now we write some small code to make the API calls. So you'll recall from examining the structure of the response on AfSIS DB, the results come as several pages. And each page I'll want to store as a data frame in R, and then I'm going to merge all those data frames together so I'll have one big data frame for an API call. So first, how will we construct the data frame for a single page of results? Well, that is shown by this code right here. This is not going to be a talk about how to program in R, so this is kind of assumed that you know something about that already. But basically what's happening here is you're going to get many results from the response, right? And what we want to do is apply this function, that's this lapply. We're applying this function here to all the results in the content. And what this function is doing is it's saying if you see something that's null, I'm going to replace that with the NA symbol in R. So I'll have a nice, well-structured data frame for a single page of results. Then we need to call this rbind API call function over and over to merge all the results from different pages. So this is the main function we're going to be using henceforth, API to DF, API to DataFrame. So it takes the URL, the username, and the password, right? And you're going to make your GET call to the URL, authenticating yourself. This is the API call function that we wrote before. So it makes one call to the API and to get the first data frame from it. And then in all the subsequent pages in this for loop, we keep making those calls, and we're going to merge all the data frames together to make one big data frame. This is not necessarily the cleanest R code in the world. Personally, I prefer to use Python, but it'll do, and you can adapt it to meet your needs. We also insert a progress bar so that we can see how we're doing. So let's actually execute all of these cells of code. So now they're stored in the memory, just to show you that it's actually there. Let's try it, API to DF, and we can see that this is a function defined like this. Okay, so let's test it. So let's try filtering some of the search results, adding some more parameters to the URL. So here is a listing of machines that AfSIS DB currently supports for spectroscopy: the Bruker alpha, zinc selenide alpha, potassium bromide, MPA, and HTSXT. So let's say I only want to see the results that correspond to the MPA machine. So in the language of these APIs, what I would do is add machine equals MPA and some additional parameters to this URL. Okay, so it's always the same base URL here. Well, it's actually this part is always the same. AfSIS DB QED.ag/cabinet/API, and then this next part is which table you're looking at, such as wet chemistry or sample in this case for spectroscopy, right? And then you'll have a question mark, and you can add some parameters like machine equals MPA, or down here, group equals TANSYS and machine equals MPA. Then you're going to plug it into this API to DF and press enter. And as we can see, the execution is running. We have a little progress bar telling us how far along we are in executing this query. And yeah, 63%, 65%. So when it's done, we'll be able to run this line here, where I basically just print the, well, I invoke this str string command on the data frame, and you get some summary statistics about the data frame, right? Okay, so just a few more seconds, and we'll be able to run this. Okay, it's done. So let's take a look. And we can see there are 722 observations of 7 different variables. So these are like the columns. We have the SSN, the machine, they're all MPA, subsample IDs, scan date, binary file, which has links to the S3 buckets where you can download the raw files, is a public, and the group levels. Okay, great. So it works. And similarly, we can do a query for find MPA records that are affiliated with the TANSYS group. Okay, and then I'll press enter, and this will execute. And this is a much smaller set, so we're done already. And then I can take a look at the data frame, and it's similar. Great. So now, what's left? Well, we may actually want to download the spectral files, right? Maybe you're trying to build a model in which you're trying to learn the relationship between the dry chemistry spectral files and, let's say, wet chemistry files, right? So you want to build your own because you want to go beyond the partial least squares technology that comes with the Opus software. So then you'd actually have to download the spectral files and have some means of processing them and parsing them. Okay, so that post-processing is beyond the scope of this video, but I will talk about how you would at least download these spectral files. So, as we recall from inspecting the response on the website, the auto-generated URLs are inside the data frame. So, to download the spectral files, we must explicitly invoke the download operation on each URL. Okay, so that's what's happening right here in this line, download.file, right? And yeah, so you can see I take my MPA data frame from earlier, and for each, okay, so for the purposes of this video, I don't have to download all of them, right? I just want to show how you would go about downloading something. So we're just downloading the first 10 Opus files from this data frame. So from I is from 1 to 10, I treat this, as a string. I download it using the curl, and I can specify a destination for the file name. Okay, and so then we have this line of code. It's not really necessary to download things, but we're specifying that the file name should look a certain way. We like it if the file name looks like ssn.subsample ID, and that makes it more uniform. The reason we're doing this here is simply due to some inconsistency in the way that different labs name their data, right? So, maybe eCraft has a certain ICR prefix that it inserts in front of all of these things, but then the same sample might be analyzed at another place and not have the ICR in front. So unfortunately, it's just a very hard problem to unify all of the labs that use a single ID, like those on tag.qed.ai, for example. So then we have to resort to these kinds of hacks to kind of force the names to look a certain way so that we can stack the data more easily. Okay, so let's try running this. Again, it's really simple. It's just a for loop with a progress bar and some file name hacking here. Okay, so we can see that my download is almost, well, it's moving. I can go to the terminal here to see what's going on. And lo and behold, yes, there are files being downloaded right here. And there's more and more of them, right? Yeah, here's another one, 6016. So they're showing up on my computer, and the stuff is happening. Okay, and it's done. So similarly, you can do the same kind of thing for downloading other data besides spectroscopy data, because as you recall, AfSIS DB has API support for all kinds of tables, such as, say, wet chemistry, right? So you can even specify minimum and maximum values for M3 aluminum, Malik 3 aluminum measurements, Malik 3 boron measurements, and so forth and so on, pH, and so on. And if you want more information about what all these parameters mean, there are two places you can take a look. One place is to go back to the original AfSIS DB site, right? And what we have done is that we've inserted metadata for every variable that the scientists were willing to explain to us. So for example, let's go to wet chemistry. Yeah, okay, here's some data from 1 Acre Fun. And we see all these question marks next to each variable. So I can click on these question marks and see what they mean, right? Extractable boron concentration by Malik 3 extraction, for example. What is PSI? P-sorption index. And there's also a kind of hidden feature that we are working on in which all of this information about the schema of the data is dynamically generated and is available at the following endpoint, cabinet/API/schema. This is JSON linked data, which describes all of the metadata you saw. The general idea of linked data is to provide a sufficiently rich metadata for all of our data sets such that computers can actually understand what these data sets are and link them together themselves without our intervention. Because a lot of this data is actually for computers to ingest and not for humans to ingest, because there's simply too much data out there for humans to really be able to understand it. Okay, so that pretty much summarizes my video. I'm sorry it went a little long, but I hope this provides a good introduction for how you can use the AfSIS DB API to get the data that you need. Again, you should be able to go a long way by using the regular GUI to search for data, using the search function, for example, or going to particular tables and simply filtering for the parameters that you want. However, for power users, the API is certainly the way to go. And in the near future, we hope to also release Python version of the same kind of code that you saw here. That's the end of my talk. For further inquiries, please email us at afsisdb@qed.ai. Thank you.